Repeating the step helps.
Does it work?
It is now. So, all right, guys, we are going to cover today. Today is Saturday, the 12th, and we're going to cover an interesting paper that has a lot of relevance for those of you who are interested in applying AI, especially large language models, to the healthcare domain. And I want this to be collaborative. In this audience, we have physicians, Patrick. We have people who are from the healthcare and pharma expertise. And we have
people who go to healthcare.
And people who use healthcare.
This users and product developers.
That's right, yes. With Mustak representing pharma and Patrick being a physician and the rest of us being their clients, I think we have it all covered. So this paper should be of general relevance to all of us. I'll just start by reading this paper. It came out very recently. I don't know the exact date, I forget when it came out, but it was in the last couple of weeks, I believe. Now, it has come out, as you can see, Google is involved in this. And it turns out that some of the data comes from the Apollo Hospital in Hyderabad in India. And some of the data comes from the Northwestern Medicine University. And some of the data on which the model has been trained is in the open source domain. When you look at this, you will see a pretty long list of contributors. As you can imagine, this is a pretty large project, large effort. And I suppose the abstract too is long. Yeah, please go ahead. Somebody has a question? No. Okay, so the background, the way they mention it, and I just repeat it. Obviously, I won't go over the paper line by line, and we will all collaboratively discuss. I would like to learn actually a lot from the folks with the medical background, how they weigh in on this paper. Artificial intelligence systems for medical imaging have traditionally focused on highly specific tasks and have generalized inconsistently to new problems. We know that that has been there. And then he goes on to say, the combination of large language models and vision encoders offer the potential to address some of these challenges. Have we seen this happen, folks? And those of you who have been taking the neural architectures course would be reminded, most recently we did many things. We did Videolama for videos, we did Blip to introduce the Q-Forma architecture. And that precursor to that was CLIP, the first, I suppose, very successful image text cross-encoding, cross-embedding, or multimodal embedding. CLIP was very popular. And you could do image embedding very much as you do sentence or text embedding, thanks to the VIT paper, right, the visual transformer idea, which could essentially treat a picture as a visual language. Isn't it? And so there is a lot of work behind it. And what we will do, and in a way, I apologize to those of you who are new or who are not part of the study circle, but I hope still it would make sense if you are familiar with those neural architectures. We'll very briefly cover those architectures. So the preface or the background here would obviously you would resonate with very much. The statement is the combination of large language models and visual encoders offer the potential to address some of these challenges. Right? This sentence. And then in this work, we present an approach that enables efficient training of multimodal models using routinely collected medical images and their associated text reports, and added the ability to perform a diverse range of tasks with rich expressive output. This approach unlocks a potential for a new generation of medical AI applications, supporting workflows, including high-performance, zero-shot, and data-efficient classification. So this part is important to note that supporting workflows, including many tasks, many downstream tasks. Now, if you remember, when we did the CLIP paper, do you guys remember us doing the CLIP paper? And just to whet your recollection, here is the CLIP and the CLIP2 paper. I'll just bring the pictures forward so that it will remind you, but we'll cover it a little bit. We'll review it a little bit. If you remember, this was the contribution of the Blip paper. A Blip sort of extended the work of CLIP, right? And I may not go all the way back to CLIP, but okay, we'll start with BLIP. What it did is, in its architecture, if you remember, there were 3 loss functions. One was the contrastive learning, image text contrastive learning. One was the image text matching loss term, and you added that loss function also to the collective loss. And then you had the standard language model loss. And if you remember, in the CLIP paper, we talked about using off-the-shelf vision encoder, right? Then we created an architecture whose key contribution idea was cross-attention, using cross-attention so that you could do image-grounded text, right, encoding, right? And that infused visual information into the text encoding. And likewise, because of the way these things work, it also ensured that minimizing the loss could only happen if the image encoding itself became smarter and very aligned to the textual descriptions. Right? So this was the paper that we talked about, if you remember. That will form the background of this. Now, if you remember, in this paper, we had the decoder and we had the encoder. And the big change that happened with BLIP 2, I hope this screen will take a little bit of time to load. Maybe I should scroll down a little slowly. Yes, BLIP 2's main contribution is they realized that, you know what, guys, that the decoder, now that these large language models have matured, why are we even bothering to train the decoder? Let's take a decoder that is frozen. Let's take one of the known large language models. Whatever you want to take, your Falcon, your Llama, whatever, Palm, etc. And even image encoders are pretty mature. Right? Let's take a very mature image encoder and therefore freeze it. So what it will do is it will just leave the inner 2 pillars to be trained, the text, the image, sort of base text encoding pairs to be trained, and that will be a much smaller neural network. And that was the idea of the Q-former, if you remember. Do you guys remember this paper? The Q-former, right? That was the idea. And that is the main idea that we are going to leverage. And when you train the Q-former, the insight is that you are training a much smaller beast, right? Compared to the billions of parameters of the, models like the language models. For example, this paper refers to, I believe, Llama. Using those llamas with the 70 billion parameters or whatever it is, you'll be training a Q-former, which is just a couple of, 30-40 million parameters. I forgot the exact size, if anybody remembers that. The Q-former is a tiny little beast to train. Right. Yeah, here it is, 188 million parameters. So literally 2 orders of magnitude smaller than a large language model. 2 to 3 orders of magnitude smaller. So that is what it made for. If you remember, in the BLIP paper, we talked about the fact that there's a 2-stage learning. First learning is the real one, in which you take the image, you take the image encoding, and then you feed it in that with the Q-former, and whatever comes out, the encoding that comes out, that you feed into the decoder. Right? And when you feed it into the decoder, you feed in the text, your query, and then you expect a different text. Right? You can use a decoder-only architecture, or you can use an encoder-decoder architecture. Now, why do we have a fully connected layer in between? First of all, you have to do a matrix. You have to do a linear transformation anyway to reshape the output from the Q-former to whatever is the token, vector embedding length and the token length, etc. of the decoder. You'll have to do that anyway. While you're doing it, it's always a good idea to stick in some what we jokingly call a peanut butter jelly sandwich in the sandwich, right? A few fully connected layers. And then, and the same thing, if you're doing both an encoder-decoder language model, then no problem. The same thing you feed into the encoder, it will go down to the decoder. The only thing is that you break up the label and the input as prefix goes in, and the label is the second half of the text goes out. So I won't cover this. We have done this. Suffice is to recap how well it does in some of the classic tasks. For example, look at this photo. Is this photo unusual? And it came back and said, it is a house that looks, it's upside down, right? How would someone get out of the house? And then it says there's a slide next to it. These are the things that were generally not quite possible a couple of years ago. These are all very recent developments. You can see the convergence, the power of the large language models being brought to harness along with very powerful visual encoders and in between a Q former. So it's a complex architecture that puts many strengths together. And
so who's asking those questions? I mean, in what context?
Oh, you just give it a picture and see, remember in this is what is the multimodal learning. So you're saying, here is a picture and here is a question and answer it, right? And isn't it amazing that it can do that?
It's like a chat version of that.
Exactly. It's a full language model, and you can use it because of the decoder, because of the generative nature, right?
And this is blip user.
This is the blip2 architecture.
So this like you feed the image and it gives you like almost a good, much better description, right? That's what you talked
Indeed, it gives you a much better description. And we went through that, if you remember.
You said like you can generate labels from it.
Yes, you can generate labels from it. And that was the original blip paper itself, if you remember. Let's scroll back. I know, I apologize if it looks scary, like me, like giving you vertigo by scrolling up and down. But if you look at the original blip paper, because of this, if you, and just to recall, how much better does it do? Look at this image. Remember we did this image better, oh gosh. This picture came with the caption, "From bridge near my house," which isn't very descriptive of this picture, but a blip generated a very different caption for it. It said, "A flock of birds flying over a lake at sunset."
That's where, like, where would you then use this? Like, let's say this text that's generated.
Yeah. So in a way, this is it. Alexa, today's work in healthcare is a very clear demonstration of how you can use this powerful architecture. Right? Which is why I picked up this paper, because I thought it's for us, practical. Of all people, for us guys who have taken the neural architectures workshop, this paper should be dead simple to understand. We should finish it within an hour, and you'll realize that it is in many ways just a domain adaptation of blip2 to this domain, to the healthcare domain and healthcare data.
So Asif sir, I have a question. So the thing about healthcare domain is radiologist goes through like 7 years of medical school and several years just to figure out what an abscess is or how liver cirrhosis looks like, MRI images, CT images. So who labeled these images? And you did mention the Apollo Hospital, and it says some 2,000 images, and they're only able to diagnose this many cases. So I mean, since this seems like a very domain and subject heavy, like you really need to be an expert at reading these images, and people train for several years. What are some of your thoughts and ideas on? Yes, of course. To cats and dogs, I think people can figure that out. But when this is it requires so much heavy expertise to read MRI and CT images. What are your thoughts on how good or in terms of labeling the data set involved and how we're actually processing these images to get to this endpoint? So that's all the question I have.
Shalini, thanks. Actually, that's really the perfect question to ask before we start on this paper. So let me try to answer it, and maybe Patrick can weigh in and Mustaq here can also weigh in. So here's the situation. The bad news and the good news. rewind back to the start of the pandemic, 2020. The AI community was, with all the confidence that engineers always have, right? I always jokingly say, if you ever ask an engineer, can you solve this problem? He'll always say, of course, even before he has looked at the problem. Right. So with all the confidence that we engineers have, we were sure that we could create a diagnostic tool using AI for detecting COVID by looking at lung x-rays and so on and so forth. The reality was that actually it was a uniform disaster. People can say we didn't have proper data, we didn't have this, we didn't have that. But it may also be that the state of the art wasn't advanced enough. But the reality is that the only test people could trust was the RT-PCR test that most of us went for. It was the gold standard. It was painstaking, it was a little expensive, the government covered it and made it free for us, but it isn't as instantaneous as, for example, having walked through an X-ray room and having knowing the diagnosis right away. It didn't rise up to the clinical standard needed for a wide deployment. That was 2020. I don't know how we would look at the situation today because the state of the art has moved forward. The problem then was, the genuine part of the problem was, I think, two parts. I think the state of the art needed to move a little bit more forward before it could be solved. And the second part was that genuinely data was hard to get, and it was chaotic and it was noisy. And it was very difficult to train models. Some people tried actually, but I don't think they succeeded very much at all because it was never widely adopted. But the second part of it, that is one aspect to it. The second aspect is, see, most of these battles are fought incrementally. These models are getting better and better. We are all moving towards the tipping point. Have we reached the tipping point? I don't know, but are we close to the tipping point? I think we have it seems as though we are pretty close to the tipping point. Now, I say that with caution. For example, in nuclear fusion, being partly a physicist, in nuclear fusion, all the physicists are sure they're close to the tipping point. And they have been sure for the last few decades. Right? So it's like peeling an onion. Every time you solve one problem, the other one shows up underneath it. So we don't know whether AI is very close to cracking the healthcare in a significant way, or it is a battle of attrition. We'll first solve the easier problem. I do know that it is beginning to solve a lot of there is a subset of problems that are solvable, and AI is beginning to make a non-trivial contribution now. So the things are beginning to happen, but have we reached an inflection point? Time will tell. But one thing I must say that 2023 is the year when a lot of those ideas have come together and started yielding fruits. It's almost like years of research now finally has reached a level at which all the pieces are beginning to come together. Like this paper, BLIP2, if you look at the date, June 15, 2023. When did we cover it? My guess is we covered it in July. Right? In July, as part of our course, we covered it. This paper, Elixir, which uses this, literally is a domain, in many ways, a domain adaptation of this paper, has literally come out in, what is it, August or July end? Patrick, do you remember when this one came out?
Elixir, as if it's here, it was published June 15 there on the paper. So
oh, June 15th itself. So obviously these guys must have been communicating with these BLIP guys. How can you publish the same thing on the same day? Oh no,
Elixir, Asif. No,
yeah,
Elixir
yeah,
was I think less than a little over a week ago.
Over a week ago, yeah, that is it. So guys, you see how fast things are moving. So
Yeah.
that is one aspect. The other thing, Shalini, to your question is, see, it is not magic. These large language models, at the end of it, what are they? They're calculating machines that use calculus, right? The magic of calculus, the magic of linear algebra and probability theory, and good architecture, good solid computer architectures and hardware and software. Many fields of engineering and mathematics have come together, yes, but they are being taught by great experts. All these models are being taught on what? Years and years of narratives, explanations medical notes that physicians who have gone through 20 years of training, 30 years of training, radiologists, and those are the people who have written notes. And in a way, they are the educators for these large language models. It is their intelligence, their wisdom, their experience, or whatever you call it, that is being distilled into this model. So the fact that these things are enabled literally is a gift of the vast armies of radiologists and physicians who wrote those notes.
Hey, Asif, this is Shivani. Just wanted to chime in on that part.
Sure,
Actually, in the field of medical imaging, this not using the large language models, but the earlier modes of machine learning, it's very prevalent. We work on optical coherence tomography a lot because we are basically in the eye space. And we have employed reading centers that have their own NLP algorithms and CNN networks, things like that, the ones who have neural networks that are actually training. These models are trained on reading images, whether they annotated for physicians, from physicians, or annotating it by themselves. And then they are providing, because to launch into our clinical trials, we basically need it in the form of data as well as image, and it's translating it into data, and we are sending it for submission to the FDA today. That's happening, right? In addition to that, for the radiologist part of it that you were talking about earlier, that's why this paper is very interesting. Using DICOM standards at the back end and using the radiology standard template reports that are available, there's a lot of play that's already been done in the AI and machine learning space, where folks have tried to take the PACS system, right, the picture archival system that runs in hospitals, and before they generate the report, apply the algorithm to it, and then so that it can aid the doctor or the radiologist in making better decisions. So both of these things are there. I think what's not happened yet is applying large language models.
So, Shivani, thank you for that. So is it okay if I can say something?
Yeah.
Yes, please go ahead.
So Shivani, you said it's the PAC system. I think this was about 10 years ago when this was my first postdoc at Stanford, which was doing exactly that. You said it converts it to data, and there is some set of transformations that are happening. Is this via GE? Is this something that I know a lot of time people publish patents, not exactly papers. Is this something that, we can look up or something we can see? And and I know Asif sir mentioned that, a lot of radiologists are annotating it when, I believe him that we're headed in that direction. But we did have a, let's say, a presentation at work where, my focus, I did do radiological imaging, but I also did a lot with material science. The funny thing is we had a presentation at work and somebody was talking about drugs, and what they presented through the large language model was cyanide, which, is kind of poisonous. So it was kind of funny in that sense. So it's, my project at work is hallucination with these large language models. So I guess I'm just asking, is there some place, not that you need to give us the exact description, is there some place where we can read more about how field has progressed? Thank you.
Yeah, sure. Yes, there is, and there are papers that are published. But as I said, they are on the earlier architectures, and I can share that.
Actually,
Go ahead, Mr.
actually,
I wish I could give you a microphone. Would you mind actually coming here?
oh, yes.
I'm sorry, I'm making some arrangements, guys, so that we can hear the audience here also, but I'll request Mustaq to come. Mustaq, sit down.
No, that's okay.
You just want to sit down.
Yes.
Yes.
I'm okay.
You have to
Okay,
be
that's fine.
literally into the microphone.
I think also if you look at Google has done a lot of work in this whole imaging space. And so they used to have Google Health.
Yeah.
I don't know what it's called right now, but they actually partnered with India and some of these remote villages in India, collected like a lot of the images and developed algorithms. And then also like in digital pathology, for example, it's different type of images, DP images, but same thing. We apply the traditional models, I call them, right, where you can then find out patterns from it, right? And same thing with oncology where we have these tumors and we can like really look at the tumors and see like where the tumors are and how much is the tumor burden. Right? I feel like reading this paper, the big difference is, and we'll see when as we go through it, is what we did not have was converting that to text that was meaningful for humans. I think that's the probably link I see is that now you could actually understand what's happening in the tumor, but then hopefully the model can then also write a report, which was not the case before, right?
Yeah.
So almost like linking the language to the image is like something that now, with these new models you can get it, right?
So I think for in this example, say something like abscesses, which I did work at a radiology lab, looking at something like abscesses. So what are large language models going to do in case of tumors? And I know they have depth and dimension, and it can image in 3D. So can you elaborate in a little bit more depth? Because when I read this paper, I saw a fairly small sample set for even radiologists 10 years ago might have complained. I mean, not that I'm complaining about this paper, but as a scientist, I have to ask questions.
Maybe like let me give a different example, because I think this one is like focused on X-rays, right? But let me give a different example. So for example, in our case, we can take the different CT scans and create a whole body image, and then we have algorithms that will go into the body and then segment the body image into lung or different organs, so lung, kidney, liver, and so forth, right? And then we have algorithms that can detect tumor and then say this is like what the tumor is, right? And then there is another algorithm that can detect the total tumor burden. So that way, if a tumor is like focused on breast and if it's like spreading to the different parts of the body, and how much is the total tumor burden, right? But like if you look at all of those, it's basically other set of images or videos or numbers, right? Because tumor burden is like a number, end of the day. What we don't have is then you need someone who is a trained radiologist to go in and write the report, right? And I feel what could happen with the LLMs is exactly that. So now, given like all those data feeds and like I think the few shot learning type of things, hopefully then instead of the radiologist going writing the report, you could have an algorithm write the report. And that is like a big deal, because like if you look at the cost of doing that in a clinical trial, is like significantly higher. Like to hire the reading centers, have them like read all these kind of images, write reports. So if we can automate that with a higher degree of accuracy, that would reduce the cost of healthcare quite a bit, right? And also like speed up the whole process.
I think the only question I have is, what exactly do we need to train these LLMs with? Because even with like simple things that a lot of these LLMs seem to like make things up. They make up dependencies, they make up Python libraries that don't exist. I know while that's funny at work for something, innocuous like music, I think in the healthcare space that could lead to like a lawsuit. So if we are trying to replace these LLMs with we're trying to replace these radiologists with these LLMs who can write reports, they still have to go back and do significant editing, because even as engineers, while the projects we work on are fairly innocuous, we still have to go back and do significant editing. But we can laugh about it because nobody cares. But I think in the medical field there is people could come back and sue and things like that. So I think the question I'm asking is what kind of, I guess, the depth of the data set. What kind of data are you training with? Yes, people are like so enthusiastic saying, oh, we can train all this, but what do we have? I guess that is
if I may chime in, actually on the qualitative side, morphology and reflectivity, those are the main two things that are already predefined. They're predefined standards for measuring morphology on an image as well as reflectivity. And then on the quantitative side of images, usually it is thickness, mapping, and volume. So for example, if I'm taking the picture of an eye, what I would want to understand is the fluid volume within it. So there are already algorithms out there, there are already standards out there that have been doing it for the last 15 years. This is nothing new. So the only thing that is now changed is, like you said, if I know all of this, if I can add the agent aspect of it, which is all the analysis that a radiologist does at the end of the day, is subjectivity involved with it, we can actually reduce it to a very small degree. The review is not going to go away. The human factor is not going to go away because it is compliance at the end of the day. But it can be reduced where I needed 5 radiologists, I actually need 1.
Actually, thank you, guys. This is really great comment. Somebody else saying something else? Patrick, yes.
So should I add something?
Yeah, of course.
So let me answer Shalini. Shalini, in my current job, what I'm doing is I'm annotating the data. I'm preparing the data for training. You know, all the images, radiology images, PATH images, CT, PET scan, MRI, they have an associated report from the radiologist. So that's my annotated data already. That goes inside and machine learns from that. So then after that, you can give the machine unlabeled images and it will tell you exactly. And then this is actually me and Patrick, we are actually doing it. I am the one who is annotating the data, finding the report, trying to piece out the things which we want to feed into the machine. So here is something funny. So we have, a few days ago, we were discussing something. So we have tons and tons of X-ray. So patient comes to the emergency room and they having some cardiac problem, let's say heart problem, or they cannot breathe or difficulty in breathing. So there is a measure, you take the X-ray quickly and then you do quick ultrasound on the heart and you will know that what's the cardiac output is. So somehow by giving these X-ray to the trained model, they started telling us that this patient has this much of cardiac output. So that is a measure to whatever you want to do with the heart. If your cardiac output is above 60, you don't need to do anything. If it's going below 50, then it's a warning sign. Below 40, you have to immediately do something about it. So all the physicians in my group, they were wondering how that this machine is so intelligent that is finding out. We were thinking that there is a measure, like Shalini already I think over there they mentioned it. That is called cardiothoracic index. Like you can have a horizontal size of the heart divided by horizontal size of the chest. That will tell you how much your cardiac output will be. But we are not sure. It's a black box kind of thing. One other thing we noticed is somehow giving the chest X-ray, machine was telling us that these patients have diabetes. Suddenly.
Wait, it's telling you it has diabetes? Wait, what?
Yeah. So that's so funny. We were all scratching, all the physicians, like how you can tell by giving X-ray, the machine will tell you that diabetes. So somehow from the back end, when the data is fed in the training data, there is information that this patient has diabetes. So, this is called correlation or something like that. Like more patients who has more heart problem, they also tend to have diabetes more. So those kind of things, these models automatically learn. So that's I think hopefully answer your question. They are trained.
It's this is the thing. So yeah, have you heard of Brian Johnson? So he's the guy from Brain who apparently wants to reduce his aging or things like that. I know because he wants to reduce his.
So he's in nearby southern San Francisco.
Yeah, so it's called
telomere guy.
Telomere guy. You're right, Sukhpal. Sukhpal, we are seeing, just to chime in, we are seeing through OCT Alzheimer's.
Yeah. And then also same, I'm not going to take too much time. We in San Francisco, my boss, he worked on the brain waves to diagnose different kind of syndromes in the children, like all these different syndromes you have. So just you can have brain waves and then and his paper was quite famous. Like how you can just by taking EEG can diagnose syndrome X and other kind of things in children.
You know, I
So-
don't I don't doubt what you guys do, but I think it's the fact that we're using LLMs to write these diagnoses and
But this is in the beginning, the answer is yes, you have to feed the trained data. And we have tons and tons of trained data. You have the X-ray picture, black and white, and then you have labeled report with that. So X-ray plus report, machine will learn from that. This X-ray associated with this report, and in the impression, in the end where you see the result, so machine will learn from, start associating with that. If, if I'm correct, that's what I think. But of course, Asif sir knows more.
yeah,
Yeah,
so
no.
we'll let Asif sir, right now we're probably gonna debate over this, so we'll let Asif sir
Yeah, let's go back.
Yeah, actually, this is, I really enjoyed this discussion. You guys are domain experts, physicians, and so forth. It was really nice listening to all of you. Now, just a bit of a tidbit I'll add before I go into this paper. As you know, this company, our training place is called Support Vectors. And guess where Support Vectors, some of the best textbooks of Support Vectors are from an end user applied perspective. It's actually in the medical domain. They have been using support vector machines to study medical images for a very, very long time. Right? So there is obviously a long history of successful use of AI, and even basic things like breast cancer detection, et cetera, that we use. I don't know how much they are used in practice, using fine needle aspiration and AI, but it's certainly there in the textbook. So long history. I suppose the only question with it is, what are the big strides? Are we reaching an inflection point? And as all of you are saying, see, it's an interplay. These things are not replacements for physicians. These are co-pilots, right? And soon the table may turn. We may reach an inflection point when the physicians will become co-pilots to make sure that these things don't make mistake, and we'll rely on these things a lot more. Right? And these will become the pilot. I do feel that it will always need humans, but they'll become the co-pilots. Right? Whereas today it's much more in contemporary literature or language, it's much more common for us to say AI is the co-pilot. So with that, all right, let's go a little bit into this paper, Elixir. So the title itself says a lot, I think, that pertains to our discussion that we're having towards a general purpose X-ray AI system through alignment of large language models and radiology vision encoders. So this word is important, guys. What was Blip doing? Blip was essentially creating alignment. Blip 2 and Blip were creating alignment between vision encoders, simply put, image encoders, if you remember, VIT clip kind of thinking, and text, isn't it? And so the Q-former is a mechanism to align a video or vision encoder to a large language model. That's literally what we saw in the previous article. This very tiny 188 parameter Q-former sitting in between, forming the bridge between the vision encoders and the large language model. And it got it. And literally that's what the title says. But where is the key part? The key part is the application of it. I think Mushtaq just asked Blip 2, what is the use of, where is it applied? And literally this paper, it is almost on cue. This paper has come out, which is the application. And when you read this paper, you realize that it's a very successful application. And we'll go through that to the X-ray images. It seems to have succeeded quite a bit. And perhaps another step in making these machines, at least a co-pilot that will, for all the things that Shivani said and Shalini said and Sukhpal and Patrick and Mushtaq said, reduce the cost of healthcare, accelerate the diagnosis times, reduce the manual labor, generate the text so that it is much better to be reviewing the text and see whether, for example, Shalini brought up the fear of hallucination. Right? Is hallucination taking place? And Sukhpal brought out the opposite point. Sometimes it's not hallucinating. Sometimes it's seeing something that human beings have historically always missed. And to the great surprise, AI finds it. Right? So many, many things. There was one thought that was coming to me yesterday when I was out on my morning hike. was that these things do hallucinate. Of course, they are next word predictors. So to the extent that they have their next word predictors, at the end of it, if you ask them to produce a lot of text, they're more likely to go astray or hallucinate or do things than if you ask it to produce very succinct little bits of text. It's the very nature. See, next word prediction inherently, when you sample off the softmax, as we have been talking about it in our neural architecture session over and over again, you sample off a softmax with a certain temperature. There is a probability you'll get it right. There's also a probability that you'll get it wrong. Let's say that every word prediction has a tiny probability that it will be wrong. So the probability that it is right is less than 1 minus epsilon. But if you generate a lot of tokens, 1 minus epsilon to the power 100 is practically 0, isn't it? Take 0.99 and you take to the power 100. Actually, that was my sort of an intuitive way I always look at it, that it's a diffusion process. And so there's an exponentially rising likelihood that the machine will start going astray after some time. So I don't know how much bearing it has to the discussion we were having, but I thought that may have. But okay, let's get to the paper. So this thing says the method they use is quite literally pretty much in our wheelhouse after the course. Our approach, which we call embedding of large language image aligned X-rays. Do you see the word for embedding for language? And this sentence is a clear giveaway that we are talking about things like BLIP2, leveraging a large language aligned image encoder combined or grafted onto a fixed LLM. Fixed LLM, if you remember, the word that people used in the BLIP2 paper was frozen LLM, right? So in the frozen LLM to perform a broad range of tasks. We train this lightweight adapter architecture using image paired with corresponding free text radiology reports from the MIMIC CXR dataset. Now, MIMIC CXR dataset is sort of openly available or relatively openly available dataset. MIMIC, all of you are familiar with. In fact, we'll be using it in our project going forward. Now, let's think about it this way. When we image to text alignment, have we done that before, guys? Starting with BLIP2, we were busy doing it, right? So, and then we will do that. Evaluation of zero-shot and data-efficient classification was performed using public, text expert, and text X-rays, text ray 14 datasets, as well as private datasets from 5 hospitals in India, the Apollos. So now, when they say data-efficient classification, what could that mean? I suppose what they mean here is that it took very little data to train it. Usually to train a classifier, normal classifier takes vast amounts of data. If you see the prior medical models, the classifier models, they have been trained with a lot of data. What they are saying here is that it takes very little data to do it. I suppose zero shot, few shot, right?
Asif, sir, do you think, sorry to interrupt. I mean, this is medical stuff. I mean, it's going to affect all of our health in the future. It's going to affect all of us in the future. Do you think this is a good idea? Because there's something about this experimental design that's starting to bother me a little bit.
Shalini, that's a good question. See, in medical, the problem is, what is the baseline you're comparing to? From personal experience, once I had a serious issue, I went to 3 specialists who supposedly were dealing with that. One was a gold medalist from Delhi University, right? He gave me one diagnosis. I went to another who gave me another diagnosis. And I went to a third person at UCSF, who later on, and now he and I are good friends, a professor there. And he gave me a third diagnosis. It turns out that the third one was right. But what was interesting is that all the 3 diagnoses were completely divergent, right? So medical, see, human body, I believe some word people use, terra incognita, the unknown territory. Right? It has so far remained, quite
That's
a bit of history.
That's exactly why I'm asking, because when I was at the Department of Radiology, I mean, even as engineers, we had to go to several seminars at 12 p.m. We got free pizza.
Yeah.
All those jokes aside, I think one thing I learned was that there was a gentleman from Imperial College London who was saying that, did you know that Indian people can still be skinny and have all this cholesterol in their blood? And, I was there eating pizza. So, but jokes aside, it's also different. So how can, okay, I think I've made my point now, but it just seems so like we're all so divergent and there's so many variety of cases. How is this LLM gonna, write good reports? It feels like, we're getting, I don't know, the medical reports might not be accurate. It was written by an LLM. That's all I'm gonna say, and I'll leave it at that. I'll leave it to.
Exactly. This is indeed a good point. See, the best that I can say, and this is a very subjective opinion. If you look at the reason Mayo Clinic and Cleveland Clinic are doing much better than the regular hospital, they have a reason. We learned in AI about ensemble learning of wisdom of crowds. They literally take a committee approach to, and they have. Oh, I'm sorry, I'm getting echo back, guys. Yeah. So what they do is they will have the same patient history and observations across multiple physicians, and they sit together in a room to come up with a diagnosis, because we know that each enriches the other. And usually the diagnosis you come to collectively, the collective wisdom, tends to be, well, evidence is Cleveland Clinic, Mayo, etc. They are doing better than the run-of-the-mill hospitals. So in that spirit, I would say, consider this too. When you take in the notes produced by these AI machines, don't replace the physicians. Add it as one more member to your committee, and then come up with a final assessment in which this too is there in the committee. And as a member in the committee, I think it's a very valuable member in the committee to come up with a plan. The whole medical thing, a subjective, objective assessment plan, it can contribute to that very well. Mustaq, please.
It's funny that this morning I was listening to Daniel Pink. So Daniel Pink is one of those like thought leaders on psychology. And so he had this article on timing, and when should you go to the doctor, when should you go to, ask for a raise and things like that. And he said you should go to the doctor in the morning if you have serious medical procedures, because the human beings are more vigilant in the mornings compared to then you have like the vigilant, then you have like a throw, and then you come up recovery phase, right? So he said like I would, like if there was a serious procedure, I would go in the morning. And radiologists are the same. So what we have found, at least in our research, is they make mistakes, right? And because we are human beings, right? So if a radiologist is looking at image one, in the morning versus in the afternoon, there they might give very different outputs, in both of those areas, right? Versus machines are like very consistent, right?
Yeah.
So what we do is like, if we use ML, then we have human in the loop at the end.
Oh.
So let's say, for example, if you are extracting text or structured data from medical records, you put it in the database, and then you have a human, like a nurse, look at it at the end, and so then they validate basically, right? And I think medical, at least for a foreseeable future, we'll always have like humans
in the loop. Yeah. So I'll repeat what Mustaq said, because people remote may not have heard it. What he said is that human beings have a variability of mental acuity during the day. In the mornings, if you want to get a surgery done or something serious done, go in the morning. Humans are very alert in the morning, then they have a slump, then they bounce back. Now, it turns out that the same person may give actually different diagnosis or different assessment at different times of the day, but a machine is consistent. So as he points out, what they do is in his organization, which is pretty large pharma, one of the biggest pharma, biggest pharma or second one, one of the biggest pharma in the world, global pharma organization. They keep humans in the loop. They let the machines do things, but have a humans evaluate it eventually for error. And that seems to work out very well. All right, guys. So,
Hey, Asif.
yes.
One other thing, probably this, Dilip, the AI engine could also give some probabilistic diagnosis with different options as well, saying I have confidence in this to this degree. Whereas a human may just say, this is my conclusion kind of thing. So then, in that committee that you mentioned, you can actually weigh in that input and maybe also different possibilities as well. The other thing is there is a possibility that there could be collusion between, I'm not saying it always happens, but there could be a collusion between, say, the surgeon and the radiologist, and the radiologist is just always, marking off that the knee surgery should happen kind of thing for insurance purposes, right? So if you have another thing overseeing it, then that's a good thing that the AI engine is also involved in the loop. And finally, the human could take a decision with multiple inputs, but this actually helps avoid corruption in the industry as well. So,
Yes. Hey, Dilip, thanks. Those are very insightful things. I'll summarize the two very insightful things you said. First is that physicians tend to pick one diagnosis and say, okay, this is what is happening to you. Human beings, because we expect certainty from our physician. We don't trust physicians who are less than sure. Good thing with AI models is they always give you the top 5 predictions or top end predictions, and they give you the probability score. So you can actually, and from what I know is that physicians use this. They often look at the second, third, fourth prediction from AI to be interesting. So that is one. The other thing is the collusion factor. The collusion may be deliberate, which may be like as in fraudulent. X-ray person will forever say that yes, this guy needs knee surgery because he's best friends with the knee surgeon. Right? And AI may disagree with that, right? And that may trigger off an audit. The other thing is, and again, to continue your thought, Dilip, I would also say that people always develop a group thing. Right? Human beings, to the extent that we associate with each other, we always develop a group thing. We begin to believe that some things are self-evident, which to outsiders look puzzling. And so any hospital, all the physicians are talking to each other, likely to have a groupthink and biases. They'll be much more biased towards, or very basic thing. You just bought a new MRI equipment. It needs to be paid off, right? Suddenly you see the need for MRI everywhere in every patient. So all of those things. So yeah, machines do have a use. All right, guys. So let's funnel back now to the paper. Dilip, did I summarize it well? Did I miss any of your points?
No, great. Thanks, Asif.
Yeah, and thanks, guys, for being here. This is really a fun discussion. I'm enjoying it quite a bit. So
I just had one small question, but I haven't been following the classes. But do these models even factor in the bias? Like when we are labeling data, there is, it's not always accurate, right? There could be a bias in the data itself.
Yes. So see, Heini, here's the thing. Does bias exist in data? You can just assume it is. The only defense against it is sort of the law of large numbers. You hope that over a sufficiently large data set, those biases or the errors fall on both sides of the right answer, right? And say they sort of have a cancelative or canceling effect against each other. But it doesn't rule out systemic bias. For example, people at a given time all are reading the same textbook for the same thing. They may write the same notes and they may all be wrong. We don't know. Right? So some systemic bias may still be present, but generally the best you can do, or the best vaccination you have against very overt, very gross biases to have sufficiently large data from diverse sources.
Okay, thank you.
All right, guys. So with that, we've had a pretty lively discussion. I'll go into the results, which are pretty remarkable. And remember, we are still reading the abstract. Elixir achieved state-of-the-art performance on zero-shot X-ray classification. Right? You will see these examples. What are we classifying in the X-ray? We'll see a few diagnostic categories, it will say, and data efficient CXR classification. Chest X-ray, I believe CXR is chest X-ray classification And data efficient just means that it learns from very little data, I suppose, and it gives you an AU ROC of close to 0.9. 0.89 is, let's give or take, call it 90% area under ROC curve. Now, as you know, area under ROC curve, when it is 90%, you better take it seriously. It means that something is working, isn't it? Doesn't mean it's working perfectly, but it's certainly, I mean, you would have preferred it to be 99, but 90 is pretty good and impressive. And if you can achieve that with only 1% of the training data, look at this. They just took, out of the millions and millions of images, they just took 1% image and 10% training data, 1% and 10% training data for the different conditions.
This is something academic. I'm just putting it out there. Academics tend to do this, so I hate to be the Debbie Downer here, but I'll leave it at that.
No, I mean, please elaborate a little bit more on that.
So, this is the thing. So, when I was at the radiology department, so this was at UC San Diego, it was funded by GE. So it was a radiology lab where we're looking at pulse sequences, machine learning and things. So that is kind of what started my PhD program. So when we're looking at this, a lot of what they realized was that each person was different, because what they realized, because we were in San Diego, there were a lot of people of Mexican origin who had high fatty liver, even though they did not have the alcohol problems, but Caucasian people who had the alcohol problems had fatty liver. So there were people of different genetics with different. So when I look at this data set and they're telling me this kind of feels like they box something into, they're not telling us all the questions. I'm just being honest with you.
It is true, Shirley, if I may put more color to what you said. Recently, there is a lot of attention being paid on the quality of the training data. You do, what you say is right. These images, to the extent that they are derived, for example, there is a huge bias towards the Indian subcontinent because data has been gathered from the Indian subcontinent. And from
Apollo, which is the funny thing about Apollo, it's all the way, it's a pretty big hospital.
It's a big hospital and it's a little bit caters to the affluent crowd. That's right. So obviously, are we finding things that are specific to the affluent Southeast Asians, or are we finding things more general? At some level, the truth has to be somewhere in between, right? Ultimately, the human body has a uniform structure, but there are specifics. That is one. And so, I mean, Shali, your point is absolutely true. In the sense, these days, as people are looking into data, they went back and look at, I believe, the ImageNet and other CPAR, etc. data, and they realize that it's a disaster when you carefully look at how many mistakes there are. And there's quite a bit of effort these days to clean up the data. So yes, with that is true.
Asif, if I may chime in on both the points. On the point of diversity, actually, FDA requires, so these drugs come through clinical trials at the end of the day. And it is absolutely required for us to have diversity in our clinical trials. So there's a big push on the drug manufacturers right now to have that diversity so that it's not just tested on Caucasian populations or Asian populations, so on and so forth. That's one thing. Second thing, I think, Shalini, you brought it up again and again, where you're saying that everybody may have different genetics and different demographics, and that may impact how the drug reacts in them. So the whole push in medicine, as far as the pharma and life sciences is concerned, is towards personalized medicine. And this personalized medicine has already been tested. It is tested on a small scale.
I strongly disagree with you on that 100%.
I'm sorry?
I'm sorry. I don't believe that 100%.
Let me complete my sentence and you might after that. So the way the personalized medicine is working is not person by person. That's not the meaning of personalized medicine. What it means is powering one's own immune system to fight diseases. So they recognize that everybody's immune system is unique. They recognize that everybody's genetics is unique. And therefore, cell therapy is one such measure, which is very predominant in oncology currently, which is one-to-one. So you take the cells from a cancer patient, you inject it into a hamster or a subject that can take it, and then you grow the antibodies there, and then you give the antibodies back to the patient. This is a very common thing in oncology. It's also picking up in HIV and all of those things. What the next generation of medicine is doing on personalized front is to take it mass scale. So that is the holy grail of pharma and where they're trying to do right now. And all of us are striving towards that.
Okay, guys. So yeah, this is nice for the very lively discussion. I think it's going to be a fun reading. So let's move forward. Actually, this is amazing. So much different experience and deep experience and deep perspective. And Shivani, thank you for being here. This is a pleasure. I think it's the first time you're here. I hope you'll find it fun and be here again. So, and today, how many new people do we have, Shivani? Thank you for being here. And anyone else who's new here for the first time for the paper reading? No, we have all been. So it's a fun community. Thank you for helping us out. And so, guys, I'll just go and give this finding. As you can see, I mean, the data being as it is, with Shalini being a little skeptical on the data quality, and Shivani is giving us much more detail on the FDA regulations on the data and how it has to be applied. With that, which is quite insightful, let's move forward and see what this model does achieve. Interestingly, I noticed something that is this, which is very meaningful, and I think this was a core contribution. It could have been a separate paragraph itself. It says, Elixir requires 2 orders of magnitude less data. You notice that? Less data to reach similar performance. Means, compared to prior models, you can train this with much data. Now, guys, this would all look very shocking and revolutionary. And it is from a practical perspective, but having come from the BLIP2 paper, you would all agree that you would not have expected any less, isn't it? Am I right in saying that? Knowing the BLIP2 architecture that we did in our neural architectures course, you would say, of course, it's such a wonderful architecture that when applied to specific domains, you expected to see some degree of learning, and which is what they are reporting. Now, they also go on to say, it shows promise on CXR tasks, demonstrating overall accuracy of this. So guys, those of you who are experts here, Shivani and Patrick and Sukhpal and Mustaq and Shalini, all of you, 5 of you, do you guys have any comments on this? Is this good accuracy or bad accuracy? On visual question answer.
I think you know my answer, Dr. Kumar, Asif
It's a
sir.
bad one, sir.
I'm sorry, say that again, Shalini.
I think you know the answer to that question. I saw this paper even before we started this, and that's kind of why. I don't mean to be antagonistic, but I'm very skeptical. I'll leave it at that, and I'll leave the.
Shalini, please express you. There's no antagonism.
Shalini, sir, let me ask why you are so skeptical that you don't.
I just think they picked and choose. It's kind of like, you know, it's picking and choosing. They picked and choose things, but they're not really speaking the truth. And I think that's what troubles me about this whole thing. And it's what troubles me about papers in general, which is, you know, which is.
So,
sorry, go on.
Yeah, no, I think you are correct in some way. There was a study I think last year, where it said all the papers, I think 90% of them are like bad ones. It was a big video on YouTube from Veritasium. But you know, as we have more and more curated data, so the accuracy will, you know, go up high. Sir, the question you asked, 68% is not acceptable. Usually in real world scenario, like when we are working, we shoot for a recall 95%, above 90, and positive predictive value above 95%. 5%, yeah, 5% is okay error. You know, remember that p-value thing we used to do in stats?
Yeah.
So yeah, you have to have 3 standard deviation or target nearby there.
Like I think
So
Supa, when I mean, I'm a lay person. I mean, you and Patrick have the MD degrees, but as a lay person who has worked in an engineering program, but with doctors, when I look at this, it doesn't. I mean, yes, FDA requires diversified, but people also fake results. So, I'm skeptical because I've seen things, and yes, machine learning and engineering, we can sit here and do math until we're blue in the face, but it affects people's lives. I think that's kind of the direction I'm headed.
yeah, that's actually a bad thing to do. But on the other hand, just actually, I don't know. I was watching a video. Now we have actually AI models which can detect the fraud if you are synthesizing the data by yourself. So that's also a good thing. So they will detect the bad patient, bad data, or something like that.
I'd like to say something. I'd like to say something about this. Yeah. So I think one thing that we have to bring Sukhpal to the front to the lay people is that a radiological report, it has there's 2 ways you can write the radiological report. One is just a straight up radiological interpretation of the data that you see, like essentially as if you scroll up, you'll see that they tried to detect 5 kinds of patterns on the data. They said they atelectasis,
cardiomegaly, consolidation,
cardiomegaly. These when you talk about these 5 data points,
these are standard.
Very, very standard and obvious patterns. It's really hard to miss. If you looked at a few pictures of atelectasis, you'll be able to detect this even as a layperson, because this is a standard patterns that you'd see on a chest radiograph. Yes. Now, the second part of a radiological report is the clinical correlation, which is in the context of this patient's case or condition. What is this data likely referring to? And to Shalini's point, if the radiological reports are included in the training data, and we know for a fact that in radiology, I doubt if it's still possible, but it's really difficult to distinguish like fluids difference, whether it's water with bacteria like an exudate, like pus. It's still difficult to determine these things through X-ray technology, because it will just pass through. That's why we have different modalities to do this. So a lot of X-ray findings need some kind of context, and the context that we do is we give a history. So if this patient sounds like this patient has had pneumonia because the signs and symptoms or the clinical presentation sounds infectious in nature, rather than someone with a heart problem and there's just water getting trapped in the lungs. So the chest X-rays can get you to some level, some degree of interpreting the patterns of the data. But the second part where there's a clinical correlation. So we don't know from this result from Elixir whether the clinical correlation had been brought in as part of the report, or was it just the radiological interpretation? So we need to see when they say they're demonstrating overall accuracies and annotations, whether it's interpreting the second half. If it's just interpreting the first half and we're a radiological interpretation and it's 58 to 62%, then I agree with Sukhpal that this might not be the best tool to use, because if some of these patterns are highly recognizable, then even the traditional tools that we have now from PACS are probably so much better than this for the first half. If this includes parts of the second half where there is some clinical interpretation, and that's what's causing this model to go down in accuracy, because it's trying to extend that inference to what this clinical condition is, then if you don't know if this patient has a cardiac problem or a pulmonary problem, then saying between congestion in the lungs due to heart failure versus worsening pneumonia, worsening findings of an infection, that sounds like a 50-50 shot. So being able to figure out really I think it would be good to be able to run this and see what kind of report is being churned out, to figure out exactly how well this model is performing. But it sounds good since they mentioned that they're able to detect those 5 patterns really well with an AUC of like 0.9, then I would be likely to want to test this out. When it comes to the interpretation and writing for the radiologist, that's yet to be seen. I would definitely want to run this and see how it does it.
And then Patrick, Palm 2 from Google has 95% accuracy. I'm not sure why Elixir is performing that bad. And people are using Palm 2 in real world scenarios.
That accuracy is only for generative tasks, but not overall, not in classification. That accuracy is only for a visual question answer, which is a much tougher problem.
Yeah. By the way, sir, every trained radiologist, they always write, please correlate clinically. That they never forget their life. So without clinical HPI, you don't have nothing. So
and a good radiologist will always ask for the clinical history of the patient.
Yes.
But that does lead to some kind of bias, because if you know that the patient has had some kind of infection in the lungs, then they're likely to look at this and interpret it in terms of a pulmonary infection. So AI might be good here, that it gives you agnostic, very clean data interpretation, but we don't have that second step of bringing it back to the clinical case. So there might still be another bridge that we could use here, or depending on how this model actually creates the annotations, I think we'll see the actual value in this. But without actually having like I know this paper had some examples, but those are mostly just pattern detections and just interpreting what some features, so some segments based on the question, but those are just the first half, so it doesn't sound like it's actually doing the clinical correlation. So I don't know, I have to see this in action to actually make a full assessment of how well this, or how good is this for clinical practice.
That's
quite a quick question, Asif and team. The system do the inputs have like annotated things, like where people, the radiologist circles, hey, this is the place where I see there's a problem.
Sir.
And then there's an arrow and there's some text saying what it is, or something like that.
I do believe that what they fed in was images. I don't know how many images had this like sort of boxes or annotations on the image, but they were followed with text. They were paired with text,
pointing to where the problem might be, kind of stuff. So which section of the image?
As we move forward, you'll see those examples in a moment.
Oh, nice. Yeah. Hey, but for Sukhpal's thing though, the AUC number is pretty good, right? For classification.
Yes, sir. AUC 90% is okay, but I'm talking about positive predictive value and recall. So you have, it depends on problem to problem, but actually we at my workplace it should be above 95%, but again it varies from project to project. And then sir?
Go ahead. Sorry,
I think this is a deep, Dr. Kamari, I think, Asif sir, this is like a deep thing, because it's, the data that they show, they have not been clear, they have not been honest about what they have. I'm literally right now re-looking up where they got the data set from, and it seems like they handpicked, I know I've said this twice already, but it seems like they handpicked and they put these results together. So this is why I'm kind of not impressed with this paper. I have to be honest. You know,
I think, Shalini, even if they handpicked, it's not a bad model. So, for example,
it is a bad model if they handpicked it.
no, hang on. It depends on what problem it is that we are trying to solve, right? So, I'll give you an example of a trial, right? So, I'll give you an example of a trial that we just conducted, right? And had we known that a particular set of patients actually responded better to our drug, we could have actually passed a phase 3. And this was basically a eye medicine. And in our exclusion criteria, we failed to look at one simple thing, which was how do pseudophagics, folks who've had their lenses, who have lenses, artificial lenses, how do they respond to our drug? And because we didn't put that in our exclusion, now I'm being very specific, because we did not look at that population, what ended up happening was the whole trial failed. But when we segregated the trial for only the pseudophagics, our drug actually performed as well as our standard of care. So it depends on the use case. It depends on what it is that one is trying to achieve. So even if this proves, even if it is handpicked, but it proves a particular concept that is of value, it can be adopted by some of us where this value would actually be realized. So we can, generalizing it that way may not be the right approach, because it depends from use case to use case.
Yeah, also Shalini, maybe not all the inputs are not useful.
I'm not asking for generalization. I'm asking more for delineation. If that makes
Shalini, some inputs may not have the adequate information. Maybe they don't have the annotation. So you have to filter them out and then take the ones that actually have all the information that feeds both image, text, correlation, information kind of thing for training. So may have to select, for training.
No, I'm
to be waiting for some time with
no, we'll let you go, Asif, sir. We're so sorry. We're so sorry.
No.
We are so excited today.
Yeah, it's a very stimulating. But I want to give Mustak a chance, who's been waiting for a very long time to chime in. Mustak, please go ahead.
I think all I was going to say is, I feel like this AI is, I call it like traditional AI, and this new models and everything. It's like almost like a step change that's happening. And to me, I look at this paper as, one of those things that you do on the road to a longer road, right?
Yes.
And I think it has like some good elements of it. We could argue about the accuracy or not, but I think it's something that we could say, okay, now you can see the potential, and hopefully people will build on top of it. Right?
Yeah.
So I'm assuming the pharma companies and medical community, and they'll start using this as like a stepping stone, and then run their own tests and then continue to build on it. So I think to me it's just a step in the right direction.
Yeah, I'll just say what Mustak said, because people remote may not have gotten it. He also chimed in with something insightful. He said that, see, it is clear that with these large language models coming up and these transformers, there is a step function effect compared. We are able to do things that we weren't able to do before. That is it. He also pointed out that, see, this paper is a step in the right direction. It's certainly a valuable step. We'll get there, but it's certainly a valuable step in the longer journey that we go to. And I suppose, see guys, this is the fun part. We have different perspectives. It's lively. I would like to a little bit summarize it. My own perspective is, and obviously I'm not a medical expert, so you guys know better. My feeling is, knowing the BLIP2 architecture, it was almost like lovely application of BLIP2 to the healthcare domain, and the fact that it works. So I would not doubt that it works. I think it's and I personally wouldn't doubt that it's a significant contribution to this space and adapting it to the healthcare. There is some skepticism that Shalini brings, that whether people cherry pick the data or honestly. Let's hope that by the time this paper gets peer reviewed, we have a different set of results, much more rigorous results, and they will come through. Also, to Shivani's point, in general, in this space, highly regulated industry, papers being papers, but by the time it actually gets adopted in practice, the FDA will make sure. FDA standards are extremely rigorous, as all the pharma, I can see here, Mustak shaking his head. Pharma companies know it's very, very high bar, very high bar to meet. So by the time these things actually go into practice, obviously a much, much higher bar will be met. But certainly, I mean, when I look at it, researchers, I mean, think about it, the guys who wrote this paper, they are AI scientists, right? They make do with whatever data they have access to, and perhaps there's a little temptation to maybe cherry pick it or not cherry pick it. I don't know. I am not qualified to speak to it. But certainly it looks like a good contribution. But with all the
Asif, general input though regarding the, you were trying to echo what the audience is saying. I'm hearing them loud and clear in remote. So your microphones are working beautifully. Where they're picking up the audience very well. So.
Oh yeah, okay. So you're picking up Mustaq also. Wonderful. So I won't repeat it then. Nice. All right. So any more thoughts, guys? It's lovely that we have such divergent views because makes it. Let's move forward.
I think it would help us if we go through all of the in terms of an engineering detail, because I have a feeling that we will get down and fast in terms of the debate, because I've read.
Yes. Yeah, the debate is not for us to resolve. And I think the best debates are never resolved. It's good to continue having different perspectives. But yes, let's get into the technical detail. So one thing that they mentioned, which to us, for people who have been taking this, we have been going through this whole process, we know that this was almost inevitable. This statement, using a traditionally fully supervised approach, training CNNs and vision transformers is an expensive and time-consuming process that requires large quantities of expertly annotated data. True, isn't it? We have known that is true to pre-train, and we would use the word pre-training those models takes a long, long time. And training it for a specific domain after that, fine-tuning it also takes a long time. So what they are proposing, at some point they say so explicitly, that they're using the blip and adapting it to it. So I'll just read out the key points. We described the key advantages of Elixir, and now we are going into the technical aspects of it. Elixir achieves state-of-the-art performance for zero-shot classification, right? Which is interesting. It does some classification without further notes, data efficient classification. And here, obviously, there's a bit of caveat that Sukhpal and Patrick brought in. They seem to have picked some of the easier things which physicians are perhaps would find it. The radiologists would find it more their 101 level stuff, but it seems to be getting it. Semantic search of thoracic conditions across the range of data sets. It's still good that it got there. Adapting an image encoder to an LLM using Elixir is a fast and resource efficient method of training. A resource efficient, fast and resource efficient method of training compared to. So guys, if I were to ask you just as a question about understanding the neural architectures, where do you think the fast and resource efficient method part is coming from? Knowing the blip architecture, what would you ascribe it to?
The Q-former.
The Q-former, excellent. This is great. It is the Q-former that sort of.
Why is that?
Because remember that what it Q-former, the blip2 basically says that get a great vision encoder, get a great language model. Let us just align the two. The Q-former aligns the two. So it will be obviously fast, and because it's only 188, like the original Q-former was 188 million parameters, right? Much like today, it's almost like a baby model, right? In the world of these ginormous models. So it's a fast and resource efficient method of training compared to full fine-tuning of today. When you hear the word full fine-tuning of LLM, like after learning about all of this, Q-formers, distillation, LoRa, Q-LoRa, etc., you would almost ask like, okay, have you thought of all those things before fine-tuning a full LLM? Those are the natural questions one would ask, right? And so here, obviously, the Q-former is the approach they have taken. Now, building models on top of the Elixir can be done rapidly to prototype new use cases. So this part actually I like. Remember that a good work always opens the door to more work, and I like this part. Though it's not. So we can take this further. I went to Hugging Face and saw if this model has yet been released. The Hugging Face link, it gives you a link to the paper and the abstract, but so far I didn't see the model there. And I don't know if anyone has information of whether when or if this model will be released to Hugging Face. Anybody knows, let me know. So Elixir's synthesis of image and text unlocks a new generation of medical applications. So this synthesis, of course, comes from that.
I think this is synthesis. I mean, do you bank on your word synthesis? This is synthesis between two different groups. So I think this will be released, or somebody will release it, and so on. Yeah. So
Okay.
you will.
Yeah, nice. Yeah, let's see, Shalini, when it comes out. I'm eagerly looking forward to it, at least.
As I said, what does it mean by building models on top of Elixir?
Means further adapting it.
Further adaptation.
That is it. So think of it to further fine tuning, or using this and putting something before and after or something.
I think this is a key question, because I don't want anybody building models on top of Elixir unless it is certified by a whole bunch of doctors. I'm sorry, but this is really troubling, because I'm a human and I might have health issues.
Yeah. No, Shalini, see, your point is valid, but there's also the opposite thing. Right? Researchers can do whatever they want because they have the license to explore and experiment and so forth. But we have to trust the gatekeepers, the FDAs, who will make sure that these things never go near patients or in production.
Even pharma companies or hospital systems,
Yeah.
they also like reputation risks. Right?
Yeah, reputation.
And then also they want to like make sure, like, people working there, they care for the patients. There is a lot of like medical centricity that goes in.
Right.
Hey, Asif, one question for the medical experts here. Patrick was talking about 5 different classifications that was there in the introduction.
Yes. Yeah, I can go back.
Now, when we have to do correlation with the text, is there a one-to-one correspondence? Like, if you have this cardiomegaly classification, is there only one output, or there could be 5 different possible outputs? Is there sub-classifications that we have to consider within a particular class to then figure out what is the visual output?
No, you can have all of these present. So
No, you have all of these, but within the class of, say, if you classify something as, you're saying all of these could exist.
Yes, all of these could exist in a highly severe patient. Yeah,
I can answer that. So, sir, all these 5 conditions, as Patrick said, these are pure mathematical formula. You don't have to be a physician to diagnose this on X-ray. With a little bit of training, with a little bit of math, you can diagnose it. For example, cardiomegaly. Cardiomegaly is shadow of the chest versus shadow of the heart on the X-ray. So one is numerator, other is denominator, right? So by that, if that ratio exceeds a 0.65, then your heart is dilated or you have cardiomegaly. So this is how you. So yes, so when you and most of the times you said they are right directly on the X-ray or not. You don't. I don't think so. You have to directly make a cut off on the thing. When you have associated report with the picture, I think this model will automatically know this is the shadow of the heart and this is how much wide it is, and this is the shadow of the chest and this is how wide it is, and it can automatically create a ratio out of that.
Okay. So it can produce a result based on the outcome for all of these conditions.
All of these conditions.
I guess you have all possible, N choose K kind of options here.
Yeah, these are pure mathematical formulas to diagnose these conditions on the X-ray.
So any 2 of them could happen, and then based on that, the visual.
That depends on the condition. You can have a combination of any of these.
So that would be interesting if that correlation part in the system is actually picking up these combinations and permutations.
Once you have one thing, then you can keep on developing another thing.
Yeah,
right.
Nice. Yeah, and as Mushtaq was saying, it's a great first step, right? And
it's almost like a LoRa. It's almost like a LoRa for each one of these.
Yeah.
Cardiomegaly is describes the heart, so the size of the heart, and you can measure that with, like as Sukhpal mentioned, the cardiothoracic ratio. So these are things you can actually teach to non-clinicians to look out for and detect as patterns. So you have radiology technicians who can actually label these things as well. So these are not things that you have to have deep clinical knowledge in terms of calling it out.
So over time, you should be able to, I mean, if this is mathematically determined, over time, the system should be able to improve its visual output, right?
Yes, for example, for example, right now in image search, what do we keep on giving the images of dog, and ultimately AI learns that this is a dog. So if you keep on giving images of chest X-ray again and again and again, it learns that this is the heart.
Yeah. So hopefully Shalini will not be misdiagnosed.
No, soon I'm telling you, soon we will diagnose Shalini with Alexa.
Yeah, I have a follow-up question on that, if you don't mind. So from here, the journey to clinical assessment from here, what does that entail? Because that's where it can be, to Asa's point, a co-pilot for the doctor. So what are the database? What does that entail? What does it look like?
You'll need a clinical history first from the actual record. If you just give me an X-ray without any clinical history, I can only take you to radiological interpretation. If you give me some kind of clinical history, then I may be able to infer what the likelihood of this X-ray interpretation means for the patient. So
you can only go so far.
It can only go so far. So just as a straight up without the history, this will just it's like reading off of a data table. So this one's just segments in the lungs, in the heart, in the airways, blood vessels, everything in the chest. How can we interpret this? But how to infer what the data means will require some history about the patient. Sometimes if it's a foreign object, then yes, it's easy. It's easy to figure that out. But it can only take you so far, just from radiology alone.
Right. Is it true? Then those are two pillars. Then the third pillar is the domain knowledge that you have, Patrick, or Sukhpal, that you have, right? So if we had the domain knowledge that Sukhpal has, and then also the clinical history, and then these findings, that should take us very far.
Yes, but you'd have to create like an adapter to the Q former to incorporate that patient data and information. Because right now it's an image encoder. But if you're able to add that to the latent space and say that this is what the patient is suffering from, or has had a history of these things, then maybe it might be able to add those. So like as Mustak said, this is definitely a bridge, but we still need more pathways. To actually get this fully robust for day-to-day diagnostics.
So one quick
Go ahead.
Yeah.
Go ahead.
Hey, some of these, like, cancer, like people, they leave us, let's say they leave us in this physical domain, they pass within several months, and doctors only diagnose and saying, you have 2 months, 3 months, but before that, it's all very, what's the word, elusive, like people are not really clear. So I think that's the thing, yes, medical science is not exactly exact. I don't know if that's a word. But we don't know who's going to leave us with a heart attack, who's going to leave us with several other issues, who's going to get a tumor in several months, because, this is where it's at. And some of the things that are being said here is that, we were so precise and we're so concise and we know everything that's going on. I don't believe that's true. And it's fed to us so rigorously. I don't believe that's true by any stretch of the imagination. So I'll leave it at that. We are engineers, and we're trying to help everybody. I'll leave it at
Shalini, I can give you two real word uses right now. We are using it. First is incidental finding. Means we have all sorts of old X-ray and CT, MRI pictures, and AI goes into those pictures and looks for the nodule, lung nodule, and those kind of things. So we have tons and tons of those lung nodule patients. So there is a criteria classification. If you have this much of a lung nodule, you have to follow up with the patient. Those are ignored in emergency room and in regular day-to-day practice because doctors, they don't have time for every single small finding. So that's a real world use we are using right now. And other use case,
Sukhpal, you actually make a point because emergency rooms are crazy. You actually make a point.
Yes, and other use cases, real use case nowadays. Google CEO already mentioned it. It's called in our language triage. So you want to identify which patient is more serious, which patient is
triage. What's that? Triage.
Triage. Triage. So triage. So where you have, for example, tons and tons of CT, MRI taken in 24 hours, and next day you have one radiologist, and he's going to go through all the pictures and images. Well, there is no way he has, upfront classification ready, which one is more serious, which one is less serious. So AI goes first, and that it classifies the images. And as per AI, some pictures looks more serious. So it just picks up and gives the radiologist first, please go and pay attention to these first. And so then those patients can be taken care timely. So this is the real world use case. Many hospitals, I think they are using it. Triage and incidental finding. But as the models evolve,
as a human, I respect, your humanity. Where I think you made a point. Thank you so much.
You're welcome.
Nice, guys. So after all this deep discussion, can I lighten it up with a really bad joke? Not a bad joke, but a dad joke. Actually, my daughters tell me that there are degrees of badness. Then there are bad jokes and then there are dad jokes. So I'll say a dad joke. So this is for you physicians. If somebody has is a very generous person, we typically say he has a large heart. Should we diagnose them with cardiomegaly? No one is laughing. Suppose it's really a bad joke.
So it's depends on how big chest they have, sir. If they have also big chest, then they may not have cardiomegaly.
Oh,
so usually person with a large heart also has large chest too.
Yeah. So. All right, guys. So now let's get to this, the method, because ultimately, how did they do it? The method part, I thought, for us.
Sir, fourth point, please don't forget that. That's very important.
In some hospitals, we can get in and do more debates of this.
More debates. Yeah, that's right. Yes. Go ahead, Sukhpal. You want to make a point?
No. The fourth point, the one we were talking about, they actually fourth point describes that what kind of data they trained it on.
Okay.
If you go, this one, here.
Sukhpal and Patrick, by the end of this discussion, if you can explain to me, as MDs and people with a clinical experience, how you feel that they train this data, I would be a very happy person, because when I read this paper, I was fairly distraught. Not that I'm getting in your way, but if you can explain this to me, I will be a happy person. I'll leave it at that.
Yeah. All right. So Praveen wants me to mention the fourth point. So fourth point says that we are trained using paired chest X-ray and free text radiology reports, data that are ubiquitous in healthcare. So guys, whenever you see the word paired between two modalities in neural architectures, what does it remind you of? Vector embedding using contrastive learning.
Contrastive science.
So you would know that this will be at the heart of it somewhere, right? It's very much like if you go to a play and you see on the wall a gun lying, the gun will be used at some point. So, sorry, I'm getting into a lighter mode. So this is it. The expensive manual, curation by experts. This training process does not require blah, blah, blah. So let's get into that, guys. The method is quite interesting, actually. And I find that interesting because I felt that it's some of the things that you found abstract when we were doing neural architectures. You'll see how directly usable they are. So how do we train the Elixir? It is in two stages. Does the two-stage again remind you of what we did with BLIP2? The same thing, right? First, we train the Elixir C part, which is the contrastive language image pre-training. Literally, the word was waiting to show up, isn't it? Figure 1. This uses radiology reports to align our previously published pre-training supervised contrastive learning. So apparently they had supervised vision only model. So they have a model to do what? Imagine they have a vision model, a model to take input X-ray, let's just call it CXR, just X-ray, and create an embedding vision vector, right? Now, what do you need to do? You just need to align it, right, with a language encoder, right? And if you remember, the way we did that is we take the text description, and here they use, for that, they use a T5, but I suppose it doesn't matter which one you use. Those are specific details. You get the text encoding. Now, if you remember, the whole point of contrastive loss was that you want to for I and text associated with the pair, you want to minimize the loss between the VI, TI, which basically means if you take the cosine between these two vectors, VI, TI, you want to minimize the cosine, like you want to maximize the cosine. Like you want to make sure that those two vectors are aligned, right? Minimize loss means you want to, in effect, have a large number. Distance or similarity measure is cosine. Right? On the other hand, if you take it VI and a random text, you want to maximize it. That's your essence of contrastive learning. Are we together? Image is your reference. Take a text that is actually meant for that image, or is there annotated medical note for the image, and then go get a random text. Make sure that you maximize the loss here and you minimize the loss here. To do so is contrastive learning. What does that mean? Make sure that that text, random text, is as much as possible in the vector space as far. So suppose this is the VT and this is the text VI, text I. Make sure that the text, the RT, is way off, right? As far off as possible, probably in the opposite direction. Right? Once again, just to recap, why do we prefer, somewhere in there you'll see mentioned that they use a cosine distance and all of that. Why cosine distance? In higher dimensional space, contrastive learning, representation of an image and its associated text, closer together in higher dimensional space while pushing the representations apart. Right? So you can use cosine distance, usually you can use dot products and this and that, usually not Euclidean in higher dimensional spaces. But I think they mentioned somewhere that they use cosine distance.
Asif,
or maybe they're imagining it.
Asif, is this first step absolutely necessary? Or could we just use a pre-trained clip or mid clip?
No. If you could use mid clip, the idea is that my guess is, if I had to guess, what they are basically saying is that we did this step, but is it strictly like if people already have notes and text? Oh yeah, why would you want to do that? The reason for that is, okay, if you go back and look at the blip, see, this was the same question we encountered, if you remember, with the blip also. Let's go to the original blip. That will make this clearer. Oh, why has this frozen? I apologize, guys. This UI is a little bit freezing up on me. I'm not able to scroll down, and the reason for that is strange. Okay, so yeah, if you look at the original, I'm not able to scroll. Guys, OneNote does this weird thing on me, so I'll just close it and reopen it. Here, please bear with me for a moment, and I'll reopen it. So roughly speaking, the point is that it goes back to the fact that, remember the contrastive loss, Patrick. The contrastive loss is made up, blip loss. It is made up of three loss terms: contrastive loss, image text matching loss, and then of course, later on feeding on the modeling. So what happens is that just for this part, if you don't use that joint learning, then your contrastive loss and your image text matching loss will be disjoint. Right? They may say opposite things. You realize that, right? You want them to co-learn together, so that when two vectors are close together, the image and text are close together, they represent not just, I mean, both of these loss functions agree that they are similar.
So as if we use a just any image encoder without having to fine tune, or how or was this just a fine tune of an image encoder, as if essentially under the hood?
So here is my way of looking at it. Patrick, look at this picture that we covered before. If you just look at this part, right, the image text contrastive loss, right? This is your essential clip architecture. And the question that you're in essence asking is, there can be a medical clip, essentially. And why couldn't we have just used that? Am I getting your point right?
Yes, Asif. So
Yeah.
is it something that you can fine tune, medical clip, or are you stuck with whatever contrastive loss they've done?
See, what happens is that when you could, I suppose, you could start with that, but ultimately you'll have to fine tune. How will you fine tune? You want to make sure that two vectors where this loss is low, this loss also is low. Image text matching loss is also low, right? And if you remember the sentence word paper initially, what did we do? We got we used contrastive loss to quickly get results. But then if you wanted to refine the results, you followed it up with a cross encoder, right? Which was basically a binary cross entropy loss function. Right? So there is a sort of an echo of that same thing happening here. When you jointly learn, you could start with that and then start fine tuning. But the thing is, at the end of the day, you will have to do ITC, the contrastive and the image text matching. At some point, you'll have to bring those two together. That's all that is needed. So I don't know if that answers your question. Yeah.
See what it does, Asif. I think it's just I'm just not familiar with how to fine tune the clip architecture or the med clip. So maybe this has. Yeah.
Patrick, if you remember, the clip doesn't do anything. It only has. So suppose you have a vector, the text vector, text I, and you have the image I. Who is producing the image I? This is, let's say, a VIT is producing the image I, right? And who is producing the text? Just text encoding. Of course, you can use whatever you want for text encoding. Any of your bird, right? A flan T5, whatever you want. You do that, right? Then what happens is the clip is literally contrastive loss between image and text. So you start minimizing. You want to minimize the loss between text input and image input, and maximize the loss between the image input and some random text, let us say.
I understand this part, Asif, but let's say we wanted to fine tune this. Does this mean that you'd have to fine tune the vision transformer and the text, the text embed?
Effectively, you'll have to open up the because what happens is the only way you can do it is you'll have to open up the parameters to training again, right, in fine tuning. But you do have a point. Instead of starting from scratch, you can start with clip and then move forward from there, which is what sort of they may have done. They may have started. Actually, let's look at this paper more carefully. To your point, right? They may have, they have, right? Look at this. What did they do? They used a contrastive learning based supercon. Yeah. Supercon is their clip, effectively, right? Supercon is their clip trained on chest X-ray data.
Chest X-ray data. So yeah, because sir, this is important for us because we cannot train a model from the scratch. So we have to pick up a baseline and then fine tune it.
Yeah, that is it. And so they do that. And so this is it, as a person. Patrick, this is your basic, right, clip in the world of medical. And then you have a language encoder. And those two, now you can feed it into the second part. So here you notice that paired, you leave this, and then you have contrastive similarity. You do some training. What it will do is it will create alignment between the two, right?
So this opened up this was the clip architecture essentially, as if that they opened up so that the image encoder and the text encoder were the two components that they handpicked.
That is right. That is right. The only thing they have done here is they have, instead of taking a base VIT, they have taken a nicely already very good medically relevant something on medical data, so that you land much closer to the solution.
I see, Asif. So now, Asif, if we wanted to use this on something a little bit similar, like maybe an X-ray for a different part of the body, then we can just use this whole architecture, this whole Elixir C that they built, essentially.
Yeah. You can use the same architecture with one change. See, this SuperCon, SupCon, it has only been trained on the chest X-ray. So you'll have to replace it with a fine-tuned model or a pre-trained model on that part of the body. Let's say that you're looking at kidney or something like that. You will need a model, and one should presume that such models probably exist by now, because if they have done it, those guys, I'm sure that the nephrologists must be clamoring for their own model, and there must be one for them.
Yeah, CT abdomen would probably be good.
Yeah. And here is the answer for the leap search question, Surya. So image and text embedding and hyperdimensional space, they coincide with each other, right? And then you have the answer.
Yes, that's it.
Hey, for the contrastive learning,
I hear agents so much. So what are you guys using agents for? Because there are people, so we've had talks with the LangChain people, and there are people that just came into the building and said, we don't get what the value proposition of LangChain is. So I just want to know, what does the medical community think about this agent stuff?
That's a great question. Shalini, would you mind if we just park it? Let's get through the architecture, and we'll bring up the question.
Okay.
Hey, Asif, a question on the contrastive learning. The random text that's generated, that's completely random, or is it a different medical report?
It's a different medical text. What you do is, see, you have lots of pairs, right? Images and text. So your positive pair is that image, text, genuine pair. Then you randomly hop into the data set, take any other pair, and pick the text from there.
Okay.
So it's
not some from a Charles Dickens novel or
no. It's not gobbledygook or nothing from Charles Dickens, right? It is medical lingo, and that's how you train it to differentiate, isn't it?
Thanks.
It's mentioned over there. It's a free form report, medical report, right? Radiology report.
That's right.
Free form text.
Yeah. So the B part of the training is the real part, guys. So now you look at it. What do you have? You just created a image encoder, image text encoder, right? Something that it will encode an image and bring it. It will basically impose a language sort of on the image, semantically aware embedding of the image. Now you freeze it. You see, remember this frozen picture that is quintessentially there from the blip paper? It's there. Even the icons sort of match. And then what do? You take it, you feed it into the QFormer. The three losses, ITC, ITG and ITM, can somebody say what these are?
Image text contrastive loss, image text generative loss, and image text matching loss.
Exactly. Thank you. So it is what happens is that as the errors happen from the text generated from the PaLM, from the large language model, as it generates the text, you can't touch the PaLM model. You can't touch the large language model. That is frozen. You can't touch the image encoder now in the second phase. It is frozen. So all the adjustment or adaptation that has to be done is by the QFormer, isn't it? So all the back propagations will readjust the weights of the QFormer in between, right? And those three losses will be there: image text contrastive loss, image text matching loss, and of course the language. The ITG is basically the language modeling loss. What is ITG? Actually, no, sorry, I take that back. He has a language model. Oh, by the way, I should also say that, remember what we call a peanut butter and jelly the feed forward layers that we stick in. You remember that in the blip paper, the blip2 paper. I don't believe anybody outside our little study group calls it peanut butter and jelly, but I like to call it that. So contrast. So going back to this, guys, do you realize that here, this fully connected layers, do you notice that? These are your MLPs.
Some grounded text, something like that.
Yeah, so that is the cross attention part at the left. What it is when you train this Q former and the initial go to blip paper, over a normal encoder architecture, there is one additional element they introduced. It is the cross attention. Do you notice the cross attention is the one novelty that makes a whole difference in this? Where is it? It is here. Yeah. You see cross attention. What you do is the image encoding you feed in while you're doing text encoding in this pillar, the third pillar, which will later on become part of the Q former in their second paper. So the normal attention is there, but here you do cross attention between the text encoding and the image encoding that has come to finally create image grounded text encoding. So for that, we'll have
very interesting. Yeah.
Go back to a previous, and that was a key idea that this thing introduced. Right? Yeah. So all right, guys. So here we are. What is ITG? Did I miss something here? We may have missed something. ITG. Let's. Oh, image grounded text.
Grounded text.
No. It's the same thing. Image grounded text generation. ITG loss. Okay. So nothing new. This is it. Say that again, Dilip.
No. I was saying G is grounded text.
Grounded, yeah. Image grounded text loss. Which is the loss basically there. Then matching loss. Then this is it, guys. So the architecture, like if you look at the Q former and the blip2, is straightforward architecture. So what is the innovation here, guys? If you ask for it, what is the innovation? It's a domain adaptation to the healthcare domain, right? To chest X-rays. Pretty much using it. And just like the blip2, you needed a really good image encoder. They basically started with the SupCon, whatever it's called, and did its further training. And for the same two phases of blip2 are there. Now let's look at the results. Any questions, guys, on the architecture? Is the architecture obvious after the blip2 discussions? Yeah, everybody is shaking.
It's pretty obvious. I just a little skeptical about how this translates to the healthcare domain. That is pretty sophisticated. Let's leave it at that.
No, definitely, Shalini. I mean, that's a healthy skepticism because like if you look at the AI engineers, they're always confident they have solved the world's problems. You go and talk to the medical community, they have a different opinion. And that's why, to Shivani's point, that's what FGI is for, right? They make sure that.
Hey, Asif, nice pun. You said healthy skepticism.
Yes. Thank you. I didn't notice that. Oh boy, I wish my previous joke was laughed at. No one laughed at that one except me.
Can you repeat it?
I asked the Patrick and Sukpa, the physicians here, that if like in common language, we called a kind-hearted person a person with a large heart, right? So would we accuse them of what was it?
Cardiomegaly.
Cardiomegaly, large heart. So, all right, guys. So here's the thing, for better or for worse, see, one thing it does, guys, that is not argued. The fact that you can train with far less data is the power of blip2, and that power shows through. Okay. Why? Because you're training, at the end of the day, you're training you're training a few feet forward layers, but a few feet forward layers and basically the Q former. That's what you're training, isn't it? Right. And of course, you're you're fine-tuning the image encoder and the text encoder a little bit, T5 and so forth in the first phase. So fine-tuning somewhat big models, and then are followed by a training from the ground up, which is an alignment training of a much smaller model, right? And if you look at the hardware specs, it is pretty modest. The first phase, which is, see, the first phase is fine-tuning. If you look at that, what they call Elixir C, that is big thing, right? Because you're fine-tuning 2 large models. You would imagine it would need a lot of GPUs, a bank of GPUs. Then the second phase is just tuning or training the Q format. So what would you expect? It would need far fewer GPUs, just bringing it down to engineering, isn't it? You can get away with much less hardware. And that shows through in the data. But before we go into I'll go to the hardware part first. Somewhere in here is the hardware part discussed, and then we'll look at the results. Right? So let's go through the realities of training these beasts. Right? Patrick, you read through this paper. Do you remember? It's in the appendix.
It's a supplementary text, yes. Here, somewhere here. Yeah, this one.
This is it. If you look at this, the Elixir C part, the first fine-tuning part, is the big one. It was trained on the batch size of 64 across 128 GPU cores. Right? Now, this is the big deal. They used a lot of hardware to train this. The rest of it, momentum, blah, blah, blah. But the thing that sort of will get us thinking is that, okay, this is one big expensive exercise to fine tune. That's right. All right. They used TensorFlow. Then obviously, so clearly they have, obviously these are Google people. They're using Google Course and Google technology. The second part, on the other hand, we used query tokens and a max length and blah, blah, blah. Do you notice the contrast, guys? It was across only 8 GPU cores. Do you see the difference? Literally 1 order of magnitude difference, right? 8 versus 128. So, and that again speaks to the fact that Q formats are tinier beasts in between. Now the results are good. I mean, at least some part of it, to me, look, and obviously now that you guys have been in, I have to rethink, but to me, they look pretty interesting and good. So let's start looking at the results.
So, sir, if we, we need to compare it like that. If we do the coin toss, I still be 50% correct. And they are claiming 68%?
Yeah, 58. And I'm a visual QA, they're claiming 58. And for a classification, it's close to 90%.
90. That's really interesting.
That's it. That's good, right? So let's look at the evaluation of these models. AUC, what are the metrics they use? So for classification, they used AUC. So obviously and for semantic search, this is visual QA, they used accuracy, but with human judgment, like, is it accurate or not? So they would ask a human judge, the physician, to tell that the emitted text, is it a correct assessment? Is it almost correct? Or is it totally off? That's how they did that. So, see, yeah, here is it. I said that they use cosine similarity. Here is the cosine similarity to calculate embedding thing. Remember that cosine similarity, if you remember the old sentence word paper, it tends to prefer a shorter text over longer text. So dot product prefers.
Dr. Kumar, I know you highlighted this. Can you explain? Because this sentence says a cosine similarity was then calculated between the image embedding and these 2 text embeddings. So this seems a little abstract to me. Can you please tell me what you understand from this? Because I don't understand.
Yeah, see, Shalini, it goes back to higher dimension space. Typically in 3 dimensions, 2 dimensions, when we think of distance, our first instinct is to pull out a ruler and measure the distance between 2 points, isn't it? That's the Euclidean distance.
Yep.
Then we realize that if you're in Manhattan or any city, a taxi driver would disagree with you if you just pull out you find the shortest, the geodesic between 2 points and call it a distance. No, taxi doesn't go like that. All right. So they would go.
But in the imaging, in the medical community, I mean, I get it when we're going from point A to point B. I just don't get it when this person is speaking about like medical imaging.
Oh, okay. So no, I'm coming to that, Shalini. So basically, if you have an image, see, an image, here is a cat, right? Or some radiological image. It becomes an image vector. Right? And then you have a text. It becomes a text vector. Now, these vectors belong to very high dimensional space. They typically belong to 768 or 1000 something, 1024 dimensional spaces. Now the question is, you encoded them into vectors. Now what happens? These vectors, you want to impose a semantic on it, right? You want to say that I want to train the neural network in such a way that if a text and an image are saying the same thing, right?
Mm-hmm.
So for example, you see a cat jumping over the fence,
mm-hmm.
and the text says this is a picture of a cat jumping over the text. These two vectors, I want to make sure that in the embedding space, in the vector space, these two vectors are nearby. And a random text is far off. Right? So you just imposed a loss function, the contrasted loss function. So how would you do that? First question that it begs is, what is your notion of nearby? Or nearby notion, Euclidean distance or Manhattan, any of the Minkowski distances, they actually don't work in higher dimension spaces. It's the curse of dimensionality. Any 2 points are very, very far off in high dimension spaces. It was one of the things we covered in ML200, Shalini, if you remember.
Yeah, but I think we're talking about medical images here, and since I worked with radiologists, it's very confusing. Like even cancer between a female and a male is confusing even to a radiologist who's been there for 15 years. So the points, so the mathematical points might be 0.5 and 0.53. So I think that's kind of why I asked that question.
Oh yeah, okay, so now I better get your question.
Yeah.
Let's see, 2 points may be mathematically near, but from an interpretive point of view, they may be practically vastly different. In other words, it is a very subtle thing in the X-ray that makes a difference that will affect differential diagnosis. And you're right. Sometimes the training, like when you do this cross loss, it may catch it. Sometimes it may not catch it. In fact, if it is very subtle, it won't catch it. So these are not perfect measures, Shalini. You're right. These are not perfect measures, but this is the best we have got at this moment.
So the lab I was working with at UC San Diego and then at Stanford, they were working on MRI techniques that could measure some of these things, and the measures were very minute. So I asked these questions. I mean, I appreciate you in the sense that, with cats or dogs, we can really see that because as humans, we can see that. But in medical imaging, it's so minute that, only somebody with who's an expert can actually tell that. And as engineers, we have not been able to quantify that so this is my opinion, that as engineers, we have not been able to quantify that as yet.
Quite likely. I mean, at this moment, right, we are just getting our feet wet. If you look from AI perspective, it has made tremendous advances, and it has far more distance to cover. In some sense, we are just getting our feet wet. Right? We are at pretty early stages, and a lot needs to be found. It will come. So let's celebrate what it can do, and also be mindful of essentially huge gaps. Right? We are applying blunt tools to things which are very, very subtle about the human body. Your point absolutely stands. So when you look at this result, I find that very interesting. What I found interesting is that it can capture misdiagnosis. So here is an image in the results that I found quite interesting. Look at this picture. See, findings. Show me examples of central venous catheter, right? Now, not as a physician, but I would imagine that, and I don't know, but I have no idea actually what am I talking about, but most likely you're talking about these lines. Right? Am I right? This is the central line.
Yes, yes.
Right. So it did. So as a visual search, it did find the right pictures. Show me. Then laterality is important. The human body, right? People want to know left lung, right lung. Where exactly is the problem? Show me examples of left pneumonia, and it seems to do a pretty good job to me. And again, I'm not a, so Patrick Sukhpal, watch out. Tell me if I'm right. This is what it was zooming in on.
Yes,
right?
yes, this is correct.
Okay. And what it says is that these are both incorrect. I don't know why it is incorrect, but it seems to say it. By the way, what is nuanced and finding? What is nuanced versus finding?
Well, that's my question as well.
I don't know. I don't know what these terms mean, but I guess we have to read the paper a bit more carefully. It turns out that, laterality, finding both incorrect. Okay, so show me examples of left pneumonia. Actually, looking at this picture, Patrick and Sukhpal, from what little I know, one would agree that there is pneumonia, right? There are all these botches and all this congested chest there, left chest congestion. Is that right?
Yeah. So yes, sir. Laterality is correct. So there, left side is correct, and central venous line is correct in the left side. And
maybe it's saying these cases did not have pneumonia, although it's saying there is some problem with the left, but because that's why maybe finding is both incorrect, that they actually did not have pneumonia.
So the problem here is this patient is not a patient of pneumonia. This can be of a patient of CHF, congestive heart failure. So picture in both of these conditions will be same. It will look like pneumonia. So AI is diagnosing these pictures as pneumonia, but these are actually patients of congestive heart failure.
But this is, but don't you see, this is the issue that we're seeing here. This is what concerns me, because I guess.
So yeah, so this is the limitations of accurate data. You're training on very limited set of pictures here, but more accurate data you have, I think AI will eventually get more and more accurate.
I think if you have additional cardiology data, then it will correlate better, and then mark.
Yeah. 100%.
Yeah, I think that's what the nuance meant.
As if it's on the next page.
Actually, sir, I think this is
the clinical.
Shivani, you were saying something?
I'm saying as if the nuanced one is actually on the next page. What is
next page? It's a wrong picture.
It's just a pagination problem.
Oh my, sorry.
Sorry, sir. Yeah, this is actually AI is correct all the time.
Yeah, so both are correct. Yeah, it was a case of laterality. Yes, pneumonia on the left side. Okay, so this
patient do have pneumonia on the left side. If you scroll down the nuanced. Can I see the picture? What is nuanced?
One is incorrect.
Yeah.
This is what happens when people don't write their paper using later. You can see that.
Oh my God.
No, people pick and choose. Asif, I know I sound like a bad person, but it's the truth.
Okay.
Yeah, this is beautiful, sir. Yeah. So show me example of small right pleural effusion, no left pleural effusion. So we in medical school we have predefined mathematical formulas, and here AI automatically reverse engineered that formula.
Yeah, exactly. That is, see, guys, at the end of it, think about it.
So how long would it take you to diagnose this? I think that's the question I have to ask.
So so in first year, second year of med school, you have tons and tons of pictures of X-ray. So the main thing in the school, first thing is learn the normal thing. You automatically will learn abnormal. So that's the fundamental. Yeah. So if AI knows this is the normal picture, it will pick up the abnormal things. So as I said earlier, even, I give results of radiology reports, tons and tons of results and X-ray pictures. Eventually it will know this is heart, these are ribs, these are lungs, this is, humerus, clavicle bone. It starts to know that. So this is happening, same thing here. Now, in the label data for the same picture, there is one angle is obliterated. And
sorry,
no. So sorry, you go ahead.
No, so with the radiologist I worked with, he imaged my liver. I think it was the position I was in the MRI, but he said I have a huge liver for somebody my size. I'm not a very huge, but I'm not Shaquille O'Neal or anything. But we were laughing because it was imaged in a different way. So it's kind of like photography; it's in a different position. So the only thing I'm asking is that can they actually delineate in terms of what disease this is, or can it say this is normal or abnormal? That's all I'm asking.
So that's what I'm saying.
As we go down, right, it will show you. You'll see those examples. Those examples are coming.
So as you give the normal and more and more normal feed, it automatically starts detecting abnormal things. And this is how human learning works. If I know what's normal,
Sukhmal, there are key characteristics to look for, like blunting of the costophrenic sulcus, and there are telltale signs that you look for. It's
that's true.
There's a level of interpretation jumping from normal to abnormal.
So can you just delineate? I mean, since you're radiologist, so since you're MD,
we are not.
But can you delineate some things? Like I see that some things are lighter and it's a person's chest. So wow, that's sad.
That's all. It's the variable contrast. That's it. Some areas are black, some areas are not black. So that's it.
So if you go up, Asif.
Welcome. So we have one more addition. So guys, see all of this. I find it impressive. I don't know, can you imagine that something as elementary as training through backpropagation a bunch of weights, simply by looking at cosine similarity loss, right, can make it, at the end of it, this neural architecture, blip at the end of it, right, once you get the hang of blip 2, there's a lot of magic there, but once you get used to it, isn't it still totally unbelievable that it can actually do this and do it so well? To the fact that I don't know whether AI is good. That's I leave to the experts. Whether AI has reached a level at which it has achieved utility, and obviously for some things it has, as Shivani pointed out. For many things it is yet to, and the FDA hopefully will protect us from that. But I find that very impressive mathematically that we can even do this, isn't it? It's just awesome that we can do this, I feel. So. Just look at this, and it does get it wrong. So I guess this was the example when it said findings both incorrect. Show me examples of fractures, and it comes out with this. God knows what it did at fracture. Maybe it looked at this thing and called it a fracture or something.
No, bad positioning also, as if this looks like a patient who was lying down in the bed.
So, you can see the black thing at the top. Yes. Positioning is a problem. That's right.
Yeah, no, the black things just probably either they de-identified this or
right.
Yeah, so fracture can have so many variations, sir. There are 12 ribs, and then you don't know where the fracture is in the training data, right? So AI doesn't have enough sufficient sample to learn.
So it was asked for a fracture, and it basically pulled up an anomaly and just said,
So if you have, let's say, if I have 100,000 pictures of first rib fracture of first part, then AI may be able to learn and pinpoint it. Okay, now I know where the fracture is.
Yeah.
So maybe it had given some broken ribs. It would have been right.
Yeah, that's true. Yes, it's really hard because the variables are too many.
Yeah. Let's look at the next.
Asif, to be honest, Asif, Patrick, and Sukhpal, if I went to and I saw this, I would seriously, I mean, I have to be honest here. My mother is an attorney. I would seriously freak out if somebody wasn't attending to me 100%. What is this? So this is not very good. This is not putting it together. Where's the pulmonary? I mean, I've worked with radiologists. They're very detailed and they're very depth. They don't write things in one sentences. It's driving me crazy.
No, sir, you have a point. I mean, it's work in progress. It's a work in progress.
I think maybe Shalini is thinking that it's used by the physicians when they're treating the patient, right?
Yeah.
I think what I can see the use of this is more when the researchers actually looking at the images. Right? So let's say like if you're developing a new drug or if you're creating a new trial, right? And you're trying to do the analysis and see like what would work in what patients. And so you're like massive amount of data, right? So I think it's more applicable in that scenario to start with, and then at some point it might go to the physician and that other people.
Yeah. Shalini, I'll repeat what Mustaq said. Mustaq said that he believes that we are thinking that this will actually be used in practice, whereas he's pointing out that this is all in the laboratory and all for researchers.
Got it. I think even in R&D, this is rather troubling, and I don't think there's enough discussion about, you know.
Yeah, no, it is. Yeah, we should. I mean, yeah, let's.
It's like a search engine.
I'm sorry. I mean, I do aerial silks. I haven't broken a lot of bones, but I do have some concerns about that, you know. And I might be one of those people.
Shall we give AI a chance?
Okay, I'll leave it at that. Okay, I'll give AI a chance. As much as I was the original AI engineer, you know, creating, we'll leave it at that. But, you know, I'll give AI a chance. But I think, you know, with radiology, it's deep.
Yeah, it is indeed deep, Shalini. Having said that, we are making baby steps in that direction.
Hey, actually, though, radiology has made a huge difference on cancer detection, right? Tumors,
yes,
breast cancer.
Yes, sir. Incidental finding, as I said, where you know they're detecting these nodules and all the things.
As if to Shalini's point, though, it's true the way it's presented here.
Not that good.
Yeah, the physician will not be able to maximize the utility of this because it's just essentially it's looking for keywords that actually have deeper descriptions underneath the hood. So let's say pleural effusion. You're looking for something like a description, something like a blunting of the costophrenic sulcus, which is, you know how on the lungs, on the very lower outer edges, it's almost like a pyramid or like a triangle. Like on this image on the right side, you can see it's almost forming like a triangle.
Yeah.
If that starts to disappear, you know that there's water. There's water in the lower
pneumothorax. Pneumothorax.
There's
water. I have a question. Actually, I thought when I looked at this image, I was impressed, whereas you are not. When I look at this image,
I'm not. This looks terrible.
No, as if what this does is abstracted the steps to get to it and just tells you if there is or there isn't. So for the radiologist, what happens is they would add those descriptive terminologies way above, and then it would summarize into like a clinical interpretation as pulmonary edema present or cannot determine if pulmonary edema versus worsening heart failure or congestion. So those kinds of things. So as a clinical augmented a tool for decision support for radiologists, maybe it's still a little far off, but as a tool that helps us.
But Patrick,
next steps.
As any stretch.
Best use is for triage right now. So given all these pictures, let's say we have all these patients in the ER right now.
Sure.
Which patient needs more attention? So if you have all these X-ray, AI will tell you, you need to take care of the pneumothorax first.
Sure.
That's a good use case of AI.
Yeah. So guys,
Sukhpal took it home, but I think what Patrick is saying is right, which is, there needs to be some descriptive words and things like that. And I don't know if they've actually labeled that correctly. So this is, as an engineer, this is the question I'm asking.
Yeah. So if you look at this picture on the right side, so it's an actual report that the radiologist is hoping to send. It says stable appearance of right side pleural effusion, pneumothorax has resolved. This is actually just the summarize the final diagnostic, but above this, usually a radiologist would explain the actual findings, like interprets the actual signs or different characteristics of this image. So if there's cardiomegaly and all those things, they will give you a full report above. This is just the part where it summarized everything. And I understand why they made it short, because they're using cosine similarity. But here, if you look at the answer, it's just too brief. It's just saying, yes, there's right pneumothorax. So it just picked up, and it's just detecting. So right now it's just detecting the key points that it needs to focus on. So it's just highlighting the presence, absence. It's just creating essentially the segments in the imaging that are pertinent. This might be useful, but like for triage or those quick rapid diagnosis.
Quick rapid, yeah. But maybe for medical stuff, we have to find a different kind of similarity, cosine rather than cosine similarity in hyperdimensional space. Maybe then maybe we more.
Or I think we should just really test how far they're able to take this, because this is just if this is the best, like officially said, if they're cherry picking already and this is the best, then it's not really very very useful for clinics. Maybe for limited use cases. But if there's more that we can test out of this, then sure, maybe there is something more we can uncover.
Can I ask you guys, since you have been, so why is it that so when I was in the radiological department at UC San Diego, they said that African American ladies had the highest what's the word? They had the highest numbers of patients with breast cancer, which was pretty sad. And why is that? Is it their food? Is their diet? And there were some other people.
Genetic predisposition. Genetic predisposition.
Okay.
They have special kind of chromosomes and genes that predispose them for higher cancer.
Yeah. Hey,
I would need more information to give a straightforward answer in this. Yeah, I'm not too familiar.
Small interruption. Let us continue to discuss, but I'll stop the live.
Sorry, Dr. Kamari, we were just deep in our discussion.
No, it's fun discussion. Please continue, but I'll just stop the live stream, just so that.
Oh dear, did we just say something terrible?